My name is David Paquette. I'm the Associate Director of the Massachusetts AI and Technology Center for Connected Care and Aging, and it's my pleasure and privilege to be able to open up and provide an introduction to today's speaker, Dr. Longfei Shangguan, who will be talking about research on repurposing wearables, titled No One Left Behind, Building Low-Cost Wearables for Low-Income Communities. Uh, Dr. Longfei Shangguan is a grant year 4 recipient of MassAITC funding, and we're privileged to be both a funder and also to be able to hear his outstanding work in this field. He's an assistant professor at the University of Pittsburgh, where his research interests lie in the area of mobile health, wireless networks, and Internet of Things. His works have been awarded the Best Paper Award at MobiCom 2024, a Best Paper Runner-Up Award at MobiCom 2021, a Distinguished Paper Award at UBCom 2017, and Best Paper Award at TrustCom 2014. He's a recipient of the NSF Career Award, which is in 2024, Google Research Scholar Award in 2023, and he's actually has been doing research as a visiting faculty fellow at Google Health, working on AI agents currently. And he was the recipient of an artificial intelligence of Things and Systems Scientist Award in 2023. He received his PhD from the Hong Kong University of Science and Technology. And like I mentioned, he's currently assistant professor in computer science at University of Pittsburgh. So I'll keep the introduction there, and we're really looking forward to your presentation today in sort of repurposing wearables that you've done with populations in Africa and how that will translate to providing better access to Americans in rural parts of the United States. Thanks.
Sure. Thank you, David. Thanks for the introduction. Hey, everyone. My great honor to be here, present some of our past works on building low-cost wearable devices, something we have been consistently working on in the past 5 years. So our goal is trying to build something like wearables, not nice to have, but everyone, no matter where you live, worth to have. So I would like to start with a quote from Tim Cook, CEO of Apple. So Tim once said, if you zoom out the way into the future and then you look back and ask, what Apple's biggest contribution to the whole world? It will be in the health area. So that's a very bold vision, right? So over the past decades, we have witnessed that Apple, a company known for the sleeker phones and laptops, has been quietly transitioning into one of the world's most influential health tech players. So it didn't happen through hospital-grade machines. It actually happens through something as everyday as a watch, something millions of our people has already been wearing on their wrist. So this actually marks a fundamental shift. So health is no longer just in clinics. It's become personal, it becomes wearable, and it becomes data-driven. So let's zoom in for a moment. This is what that shift has looked into over the past 10 years. Back to 2015, you see the Apple Watch start tracking our fitness, tracking our heart rate. They're simple but game-changing features, right? Then came sleep tracking. And just recently, we know Apple added hearing health. So this timeline isn't just a product roadmap. It's actually a map of sort of ambition, right? Step by step, Apple start building a personal health assistant, live on our wrist, our ears, and in our pocket. So this evolution also gave us a very clear signal. Apple is actually betting big on health. But here's the question. Is this progress reaching all of us? So now let's talk about the harsh reality. So look at this stunning Apple Watch, Series 10, Ultra 2, SE, and there are also some special editions. Well, Each of these Apple Watch, has a price ranging from like $400 and even up to like over $1,200. That's actually the problem, right? Because this kind of health revolution, like smart, like sensor rich, always on, they are only happening mostly for those people who can afford a $400 smartwatch. Essentially, for many, many, especially those low-income families, like living in our rural areas in North America, these devices sounds like another planet. So let's paint a picture of the two worlds. So in rural areas in America, only like 19% of individuals have these mobile health devices, like the wearables. Well, if we shift it to urban areas, we see this number doubles. So this gap essentially is a wake-up call, reminding us of designing some solutions should leave no one behind. So imagine a farmer in a remote village, a worker in a bustling city. So having access to these life-saving tools shouldn't depend on where you live, which zip code you have. So now let's cross the borders. So in Senegal, an African country, this average monthly salary after tax is roughly like, $360. But in the United States, this number can go up to like $4,000. This is a stark contrast. Imagine someone in Dakar, the capital city of Senegal, earning this kind of like $360, then looking at a $400 Apple Watch. You see, this is nearly their entire monthly income. So how come could he afford it? So such inequity indeed not only happens on the system cost, there also happens on the technology itself. So now let's imagine there are three people wearing the Apple Watch, one from the like UK with light skin, one Native American with a medium skin, while another African American with dark skin. This device, we know Apple Watch, they use PPG sensors to measure our heart rate. But here's the catch. Studies show that PPG sensors has a bias. For those with dark skins, the readings can be less reliable. It's like the tag is seeing some of us more clearly than the others, which is definitely not like what we want. So why? Why PPG sensors have this kind of like reading bias? We know PPG sensors gonna shining a light into a blood vessel, detect these reflection signals to measure your heart rate. The problem here is that for those people in dark skins, they have more melanins inside their skin, their muscle. So when our light shining from the PPG sensor goes through our body, so this melanin gonna absorb this light signal. As a result, those reflecting signal from our blood vessel can tend to be weaker. So leading to a low SNR signal, leading to finally very low accuracy in heart rate monitoring. So if we believe, like Tim Cook, that Apple's greatest legacy will be in health, then we should ask a simple question. Who is that legacy for? Who gonna get to benefit? So that question is actually at the heart of my talk today. How do we build health wearables, not just a nice to have, but also those people living in underserved communities in our rural areas in North America need to have? So before we start, imagine that you are stepping aboard a plane where a flight attendant gonna hand out earphones with a warm smile. But here's a twist in our story. We know those low-end earphones we get for free from the earphone, from the airplane, they often end up forgotten. For example, we left it in drawers, we may just throw it into the trash bins, they get dust. So essentially, these earphones, they contribute to the growing issue of electronic waste, building up into the landfills. So now think about what if we could turn this waste into a solution? What if those discarded earphones could be repurposed, could find their new lives as a health tracker, turning a problem into a powerful opportunity? So actually, we found this is possible. Why? Because we know every beat of our heart, every breath we take, they're gonna generate these tiny vibrations that traverse through our body. So these vibrations gonna propagate through our body all the way up to our ear canal. Now imagine if we're wearing some headphones and capturing these signals, not just for music, but for health. But the problem is that we know these signals are there waiting to be heard. But the problem is like most low-cost earphones, like the kind we find in bulk and hand out on flights, they do not have an in-ear microphone to pick up this vibration, this sound. So it's more like, having a beautiful song playing, but no one is listening. To solve this problem, we are inspired by our physics principle taught in high school. We know the speaker transducer, they are built to play the sound. So essentially, they're gonna turning this electrical signal into the audio waves through a diaphragm, through the voice coil, and then a magnet. Here's the exciting part. Essentially, the same hardware can work in reverse, which means that the vibrations can move the diaphragm, creating an electrical signal we can measure. So essentially, this hardware reciprocity means that we can essentially repurpose the speakers as a microphone, sort of unlocking this low-cost way to listen to our body's vital sounds from our ear canal. So now, as we embark on this journey, let's pause a little bit to ask a few questions that will get us through. First, imagine those vibrations in the ear canal. Now think about, are they strong enough to be detected? Do they offer enough signal to noise ratio for accurate health tracking? How accurate are these measurements obtained through the earphone compared to the medical devices? Are they acceptable from medical sense? And also, how can noise and those interference can be minimized to ensure the accuracy of our heartbeat, of our vital sign monitoring? So essentially, these questions are the stepping stones to build a health tracker that truly serves everyone living everywhere. So let me first show you how weak the heartbeat signal is. So when you're playing a music using your earphone, the signal is roughly at the level of 80 to 100 milliwatt. When you're tapping your earphone, the noise showing in the middle is actually at the level of a few milliwatt. But the heartbeat, as you can see on the leftmost, is only at the level of sub-milliwatt. So there are roughly 200 times amplitude gap. So imagine if you are playing music while detecting the heartbeat, then it's highly likely that your heartbeat gonna be overwhelmed by the music, right? Because the heartbeat is so weak while the music is so strong. So back to 2021, we started exploring these research problems. So we built a system called the HiFi to answer the question. So essentially, HiFi is a simple dangle plus a signal processing algorithm, as you can see from this figure. It's a plug and play module. When you plug in your earphone and then plug in your pairing device, then HiFi can turn your earphone into a sensing module to like detect your heart rate, detect like your breath, so on and so forth. The most exciting part about this hi-fi prototype is that we made no hardware modification to the earphone, which means that for any kind of wired earphone, we can plug it into our hi-fi and start sensing our vital signs. So hi-fi on head level, it cancels the strong acoustic interference for reliable heart rate monitoring. So our basic idea to cancel this like strong interference, such as the music, is on the circuit level by leveraging a null circuit called the Wisdom Bridge. So this figure shows the basic architecture of this Wisdom Bridge. So the Wisdom Bridge is by its own design, is used to measure those unknown electrical resistance with a high precision. You can divide it on a high level into two parts, upper bridge and lower bridge. So on the upper bridge, we essentially have two resistors with the same resistance, R1 and R2. Well, on the lower part, you can see we have one trim port, C1. Another one is called the CX. This is actually the unknown, resistor we want to measure. So VG gonna output the voltage signal. So the the Wisdom Bridge works by balancing this upper bridge and the lower bridge. So how it works? So essentially, we're gonna tune this trim port until the output of VG is zero. Because in this state, both the upper bridge and lower bridge are well balanced. So the readings of the trim ports essentially is resistance of this unknown resistor CX. So in hi-fi, we are actually inspired by this architecture. So we essentially replace this C1 and C2 with a headphone transducer. As you can see here, we replace the C1, the trim port, with one headphone transducer, while replacing the CX with another headphone transducer. So we further replace the power source of this Wisdom Bridge with the audio input. So we know for any pairs of earphones, their left ear transducer and the right ear transducer would be literally same because they are well balanced to make sure their audio playback, achieve similar sound quality, well balanced. So when we plug in our left ear transducer, right ear transducer to the C1 and CX, essentially this lower part of the bridge gonna be balanced. We know on the upper part, upper bridge, R1 equals R2. So essentially the output of VG would be zero. But since, the heartbeat signal gonna propagate along these two different paths to the left ear and the right ear, so they're gonna attenuate in a different way. The impedance change caused by this signal arriving at the ear canal, left ear and right ear gonna be different. This will break this balance state of this Wisdom Bridge. Essentially, now the output signal VG would not be zero. It actually changes with our heartbeat pattern. So this is a high-level idea how this Wisdom Bridge inspired heart rate monitoring system works. So the key part here is that we know the output of VG would not change with the weighing audio, which means that no matter which kind of music you are playing, the readings of VG will not change. It only changes with respect to the heartbeat signal captured by your left ear transducer and right ear transducer. So I will skip the signal processing on the digital domain to buffer more time for the latter part of this talk. So let me quickly show you how we leverage it to detect the heart rate for our human beings. So this demo briefly shows how our system works. So we plug in our earphone into this small dangle, and then plug this dangle into our personal computer. So we got the ground truth using this device, So as you can see, the heart rate is roughly around 84, 85 like beats per minute, 87, like roughly around. When you look at the screen on the top left corner, so right above the hertz, you can see the heart rate rating 86, which is quite close, well matched the ground truth. So that's about our heart rate prototype we built back to 2021. Now that we can measure this heart rate using everyday like earphones, this is quite inspiring, right? Since it shows the feasibility of recycling those electronic waste into some like, very low cost health trackers. But this is definitely not the end. Taking a step further, can we like do more? Can we measure other crucial biomarkers that are crucial for our human health? So moving to early 2022, we start exploring a new problem. Can we measure our heart sound or what we call PCG signals? So heart sound is actually a very important biomarker to assess our heart functions, detecting those like cardiovascular diseases. So to answer this question, let's first take a look at our earphone recordings. So this is a heartbeat signal recorded by our earphone. So this is one picked up by a electronic waste we got on the like Delta airline. So we can see that the heartbeat signal are pretty like messy and also very weak. Well, we can figure out the heart rate through some like signal processing techniques such as autocorrelation, even from these very messy signals. But the crucial heart sound features, like the S1, like the S2 peaks, as well as those murmurs, are totally like, messed up, distorted. We can even not tell where it is. And it's really hard to make a very fair diagnosis by listening to this recording. Indeed, when we played it, we found these heartbeat recordings are purely noise. Like we cannot tell where is the heartbeat. So if we want to capture a clear heart sound signal, we have to figure out why the heartbeat recordings by the earphone is so weak and so messy. To answer this question, let's start from the first principle. Let's analyze how the signal propagates from our heart to our parent device, say a smartphone. So essentially, when our heart generates a pulse, generates this vibration signal, we know this vibration gonna propagate through human body, experience some attenuation, vibration, multipath effect before arriving at your ear canal. Now, when the signal arriving at the ear canal, it's gonna propagate into our speaker transducer. Now, the speaker transducer gonna transform this, earphone, transduce this heartbeat signal into electrical signal. But the problem is that since we use a speaker as a microphone, it actually has a very low power transfer efficiency, which means that only a small portion of the heartbeat signal gonna be successfully transferred into an electrical signal. So after that, we know this weak signal gonna propagate through our audio cable arriving at our parent device, like the smartphone. Here, there's still a signal power loss. Why? Because our earphone and our parent device, like the smartphone, they have essentially quite different impedance. So as the signal propagates through this cable into the smartphone, we know due to the impedance mismatch, only a very small portion of the energy gonna be successfully delivered to the smartphone. Most of the energy gonna be reflected back. So that's why the received signal becomes extremely weak when arriving at the parent device. So where's the opportunity? How can we improve the signal quality? So let's take a look at all these three steps again. For the embodied signal propagation, so we literally can do nothing because we cannot put an amplifier inside our human body to amplify the signal, for example. Well, for the earphone interface, essentially we have no chance as well because the speaker transducer itself has a very low energy transform efficiency when being used as a microphone. And we don't want to break this earphone, adding some new hardware. This gonna make the things more complicated, right? So our focus shifts to the impedance mismatch. So we were wondering, can we match the impedance of the earphone and the smartphone so that most of the energy can be successfully delivered to the parent device, here the smartphone. So to explain how it works, let's model it using a very basic circuit. So essentially here, we use a Z, which is essentially impedance represents our earphone. ZS is the impedance of our smartphone. So look at the right-hand side where the diaphragm shows this basic structure. So essentially, we know when the detected heartbeat signal propagates from the earphone into the mobile device, since Z, which is the impedance of our earphone, is way less than the ZS, which is the impedance of the smartphone, we know most of this energy gonna be reflected back, right? Leaving only a small portion of the energy goes through the circuit arriving at the mobile device. So our idea is simple. Let's add another impedance on the cable as a plug-in module, ZP. So if we can tune the ZP in a sense that the sum of ZP and ZE equals ZS, which is the impedance of smartphone, then we know when the signal flows through this audio cable arriving at the mobile device, most of the energy gonna successfully arriving at the mobile device with only small portion of energy being reflected back. So this is our basic idea. But the problem is that we know different earphones, different pairing device, they have significantly different impedance, right? So we cannot offline set up a constant impedance in hope that it can well balance the impedance of any kind of pairing device. So to solve this problem, we essentially propose a very low cost programmable impedance matching circuit. So here, let me explain the most important parts in this circuit. So essentially, our circuit features a digital trim port, which was used to adjust the output impedance to ensure that the compatibility across different phones and sound cards. So I will ignore the algorithm we are using here. Essentially, we have an algorithm to automatically balance the impedance between any kind of earphone and the parent device. Next, we do have this AC coupling. Essentially, you can take it as a high-pass filter to block those slow varying DC offset from the earphone or recording devices. Apart from that, we also have the differential amplifier to suppress this common mode noise and also amplify the detected heartbeat signal. So with all that into a small form factor hardware, we now can detect pretty clear heartbeat signal, as you can see from this demo. So as you can see from the demo that the heartbeat signal we detected with this new hardware is extremely clear, right? The SNR is pretty high, pretty clear. We can easily tell the hertz cycles, right? Well, the problem is that when we compare it with stethoscope recording, which is showing on the upper part, we see our recordings essentially lost some sort of temporal resolution, and also signal still experience some distortions. Why? Because we know signal when it passes through our human body, it's gonna reverberate inside our human body. So causing some signal a frequency selectivity. And more importantly, we know the higher frequency you have, the more attenuation you have, right? So for those murmurs working on higher frequency bands, so their SNR would be pretty low suffering. So how to solve this problem? How to make this hertz sound recordings upgrade it into a sort of a clinical grade? We then propose a digital signal processing pipeline. So let me go through this whole pipeline, explain how this system works. So the first part is still on the hardware side. So as I explained, we have the voltage detection circuit. We have the automatic impedance matching to make sure most of energy can successfully flow into our pairing device. So up to now, we have pretty clear heartbeat signal, which still suffer from some frequency loss. So we then pass it through the pre-processing and the segmentation process. So in this process, we first gonna filtering the signal, keeping all those signal below 5 hertz, 500 hertz. So this can keep the S1, S2 energy and most of the murmurs while rejecting those high frequency noise. We also leverage, for example, winner filter to sort of mitigate the impact of the reverberation multipath effect. So after that, we leverage HMM, the hidden Markov model, to segment our hertz cycles. So after each pre-processing and segmentation process, now we have well-segmented hertz cycles. We then start processing each hertz cycle, trying to further mitigate the multipath effect and recover some missing frequency component from this signal. So essentially, we are leveraging a two-step deep learning model to achieve this goal. So the first model, which we call the spectrogram recovery model. So this model contains 6 encoder layer and 6 decoder layer to sort of recover the spectrogram missing component. So here, one thing I want to emphasize is that we actually well fine-tune the kernel size here to make sure the conf can, their reception field is appropriate to capture the complete S1 and S2 component. This can improve the training efficiency and giving us a better recovery accuracy. So we leverage the standard L1 loss to measure the difference between the reconstructed PCG spectrogram and the ground truth spectrogram. So after this stage, essentially we get a PCG spectrogram with sort of a reconstructed frequency component. As you can see here, we get more detail for each signal component. But the problem is that, the phase values of the reconstructed PCG signal tend to be discontinuous, which will cause this inconsistent group delay across the frequency band. This will bring some audible noise to the PCG signals, which definitely is not good for diagnosis, right? To handle this inconsistent group delay, we then pass this through a next step waveform refinement. So here we apply this signal. We first transform it into a time domain. we then adopt a, one-dimensional UNet architecture, so still an encoder-decoder model for this waveform refinement. So we use another L1 loss to measure the difference between this like reconstructed spectrogram after the second stage and then the first stage. So this will sort of enforce the waveform refinement model to pay more attention to those like phase refinement during this waveform reconstruction. So after passing through this two-step signal processing algorithm, now we have our final output, the Hertz sound output. So here, let me play two sounds, one from our like earphone-based Hertz sound, and then another one from the digital stethoscope serving as our ground truth. So you can turn on your volume a little bit because the sound is a little bit low. So this is a Hertz sound recovered by our hardware earphone. Let me play that again. Okay, next I will play the ground truth. Then play the record signal again. You can see despite the slightly lower amplitude, their structure, their form that quite similar to each other. Essentially, when we're measuring their RMSE, the root mean square error, the RMSE is like well below 3%. We also test our system on those pathological Hertz sounds. For example, people with murmurs. So let me play it again. So first, play the Hertz sound recovered by our system. Again, again. Then the ground truth. Then our system again. So you can see they are quite close to each other. For this pathological, Hertz sound recovery, our overall RMSE grows a little bit, but still less than 5%. We also take a blind testing under the IRB approval. So essentially we invite 5 cardiologists. So here we got 25 sound clips from our system, 25 from the stethoscope, the ground truth. And then we just shuffle these 50 Hertz sound clips and then send it to the cardiologist. The cardiologist are gonna they are not aware of their origin. They don't know where these Hertz sound recordings coming from. They just base their experience to make a diagnosis. So here I'm showing the diagnosis correctness ratio. As you can see, the diagnosis based on our system, which is a white bar, and also the ground truth, their accuracy is pretty close to each other, which shows that essentially our system can reasonably recover this kind of noisy Hertz sound from our earphone recordings. Okay, I've talked about how we can detect the Hertz rate, how we can recover the Hertz sound. This is actually not the end. Early last year, we start collaborating with our partners from UMass, from UMBC. So essentially from Jeremy's group and also Dong's group, this is a joint work with UMBC and UMass Amherst, leading by UMass Amherst, for example. So we are actually measuring this pulse wave velocity. This paper just got accepted by UBCOM 2026. So here I will give you a very quick overview of the high-level idea and how we make it work. We know pulse wave velocity and the augmentation index, they are essentially reflecting this arterial stiffness, which is quite important for the early detection of our cardiovascular diseases. So currently, obtaining these kind of biomarkers require the patients to go to the clinics and then wearing these dedicated devices to measuring these biomarkers. So fundamentally, to measure these biomarkers, essentially we need to detect the pulse at two different locations with a known distance. So once this pulse is detected at these two locations with a distance, we can simply compute their pulse wave velocity. That's a basic principle. So we were wondering, could we replace these dedicated devices like with a earphone? We found it is actually possible. So this figure shows the basic architecture. So essentially we have one earphone facing downwards to our wrist, another on our neck, mirroring our pulse. So the basic idea is that we sending an ultrasound to our skin. The ultrasound gonna traverse through the skin, reflected by the arteria. So when the blood flowing through this arteria, we know this arteria gonna generate some deformation. So the heart, the ultrasound we send gonna detect this kind of tiny deformation for heartbeat capturing. So since we know the distance between these two measuring sites, then we can leverage these two detection time and the distance to compute this pulse wave velocity. So this is the basic idea behind. So I will not go through the details. So for more details, you can check our paper, I think, which will be available maybe end of this year, I believe so. So to me, I think research is not only pushing the boundary of knowledge, it's also about pushing more people to the boundary of knowledge. So early this year, we essentially I take my group flying to Senegal to do some benchmark study. Our goal is trying to show our device to their local community, let them try it and give us the feedback so that we can better improve it, and then making it a real product to help these people living those underserved communities. So, I mean, African country is not only the target we are currently talking to, we are also talking to rural areas in Pennsylvania, trying to sort of spread over our system to those locations. So this demo briefly shows our on-site measurement in Senegal. This essentially take place at a university near St. Louis in Senegal. So we try this, their medical school student try our system, and we're trying to grab some feedback. So here we grab their heart rate, and then my student help to transform these heartbeat signal recordings into the heart sound, and then we play the heart sound to the students. Yeah, they are quite exciting about this kind of technology. So here, let me give you a few takeaways on this, on-site visit to Senegal. First takeaway is that we found these wearable health trackers essentially can serve as a pretty good pre-screening tool because, the people living in Senegal, most of them are just Muslims. So the females, they're gonna wear the scarf. So usually they would not like to take it off during the clinical visit. While our system worked pretty well, even you put it on top of the scarf. So essentially, it can help people detect these vital signs without without suffering from these kind of religions restrictions. So the second takeaway is that we found actually the local village are essentially in urgent need, not only the pre-screening tool, but also the nurses. So we visit three villages near the St. Louis. We found there are on average just one nurse staying at each village. So they have no diagnosis tools, they are lacking medicines. And for this nurse, they are only get a very basic training. So all the time when the villagers come to the clinics, talk to the nurse, they come back with not very effective diagnosis. And bad transportation system also set another barrier because it's really hard to, for example, go to their capital city, to go to the big hospitals for medical care treatment. So notice that we are now currently working on some AI powered AI agent trying to help. So another takeaway is more like a meta lesson. So the villagers there shared with us that, over the past few years, numerous foreigners have visited their communities to survey the healthcare facilities. However, these visitors were often followed by no tangible support or improvement, so leaving them feeling overlooked and forgotten. So there's a deep sense of skepticism and mistrust towards outsiders. So essentially, when we were trying to talk to them, I can see they are quite skeptical. So good thing we have the local guides, he help us to translate, to help sort of fill the gap between this kind of miscommunication, this skepticism. So after this Senegal visit, we essentially initiate a bunch of ongoing threads. So first of all, early this month, essentially we got our IRB approved by the Senegal government, which allow us to deploy our system there for long-term study. And we have already upgraded our system, built new hardware prototypes. Our collaborators, last week, he, came to visit us and bring back all our devices to Senegal. So our plan is to deploy 5 systems starting at December 2025 for long-term pilot study. So 2 gonna host it on hospital to verify the clinical effectiveness, and 3 gonna be deployed on their local village. In the meantime, we have been engaging with our partners in Pennsylvania community, trying to deploy another 10 tabs of these 10 pairs of our system locally to helping those people living in rural areas. So with that, I want to wrap up on my talk, and I'm happy to take any questions. Thank you.
Thank you, Longfei Shangguan. First, I'm just going to quickly share information about our November webinar, which I think is very relevant to the talk here. And I think Anna might not get tuned
Mhm.
to the end of this conversation, but she'll be discussing work and towards commercialization of an in-ear infrasonic wearable, sort of similar concept, but maybe closer to the Apple in price point, but not really. I think it's still cheaper, but sort of how to take this to the next step. So that we're looking forward to that. But with that, I'll
Oh,
turn it over to questions, and hopefully, Longfei, you can catch that talk too.
sure.
So yeah, feel free to ask questions in chat or to unmute yourself and ask questions. Seems like Deepak is rear.
Yeah. Hey, Longfei, very, very interesting, very exciting work. A lot of real world, legwork that it's amazing to see all of that. The technical side, let me just ask a quick question. So the way you're doing the impedance matching
Hmm.
with you're still doing that, I believe, even in your final version. Do you need to do that?
Yeah, we still need to do that.
Yeah.
Yeah.
So the active probe you're generating the active probe from the speaker itself, right? So
Yes.
that is going through a different path. It's going through a skull path as opposed to sort of the body path, correct?
Uh, True. That's true.
Right.
Yeah.
So there's some mismatch in the tuning that you will get because what you'll end up matching towards is sort of the skull transmission path as
I see.
opposed to the whatever the tissue whatever else transmission path. So
I
I don't
see.
know how much that affects, but it's just curious.
Sure, sure. Yeah, that's a very good question. I mean, thanks for for your nice words, Deepak. So, essentially, our impedance matching happens on the smartphone and the earphone, right? So essentially, it's sort of balancing the earphone and the smartphone so that the signal from the cable can best be delivered to the
So you're not really impedance matching for the channel.
yeah, exactly. So that's why like we can still probing from the left, grabbing signal from the right. We are just trying to like, balance these two parts, not on the channel parts.
Yeah.
Yeah, exactly.
Yeah.
Right.
I have another question,
Hmm,
and if nobody else has, which is, so this is on the actual reconstruction.
hmm,
You use the UNet model to reconstruct, right?
yeah.
So anytime you're using a model like that, there's the sort of, yes, you've shown that it works with pathological signals,
Hmm.
but you still have the risk that these models are essentially learning the patterns in the training data, and so ultimately, they're not hallucinating, but they could um, kind of synthesize stuff that appears in the training data as opposed to for that individual.
Right. I
Correct?
agree. I agree.
Unless there's some way of, I don't know, some adversarial type of way of testing your training and so on.
Yeah. So yeah, I totally agree. So first of all, like literally, I think they cannot generate something new, right? Some like murmurs they never see in the training set. So for our like evaluation, we are essentially leveraging those like public data sets. We are trying to incorporate as much different types of murmurs as possible, trying to sort of like scale it up. But I agree with you, like, this deep learning method, I still like have concerns on the like, scalability, whether it can still scale to different unseen scenario. But yeah, I think maybe the one good thing is still like, enrich your training sites, let the
Yeah.
model see, yeah, as much as possible, right? So yeah, but yeah, I agree. This is definitely a fundamental limitation for this kind of data-driven approach. Yeah.
Okay. Great. Thank you.
Sure, the back. Yeah.
There's a question from Joe in the chat asking sort of when with
Hmm.
smart rings and other devices becoming cheaper, sort of allowing other modalities,
Hmm.
sort of like in the long term for a cheaper headphone type thing, does that sort of what is the benefit to pursue it? What does this give you that you wouldn't get potentially through a smart ring? And then he's asking, is dark skin the color, the issue being overcome?
Sure. Yeah, that's a very insightful question. So first of all, I agree with you. If like, we can, get like $10 or less than $5 ring to detect all these like, biomarkers, then definitely we should go with that, right? It's cheap enough. The problem is like, for now, we still not see too much like, those very low end, like, health trackers can enable that. So on the other hand, like, our methods, despite its low cost, it's also trying to solve another electronic waste problem, right? This is a sort of like a design paradigm. Like, not only provide you a low cost health tracker, but also helps to like, minimize the impact of those electronic waste, right? So yeah, on the other hand, yeah, you also mentioned that is dark skin color the issue being overcome, right? So for the smart rings, they usually still use a PPG sensor, which like more or less suffer from the like this skin tone issue. But for audio-based solution, we have no this kind of problem. So this is also another benefit of this audio-based solution. So long story short, so audio-based solution, we can make it low cost. We can like, we suffer less from the like, skin tone, and also we can sort of addressing the electronic waste problem. Yeah, I hope I answered your question.
A question for Misha.
Hi. I might have missed it, but in your recovery portion of your signal, it looked to me like you were doing neural network or something.
Right.
Was that correct?
Yes.
Well, I was wondering why aren't you using some principled approach like Wiener filter to, optimal filtering technique to recover the signal?
Sure, sure. That's a very good question. So essentially, we are using some conventional signal processing algorithm like Wiener filter to reverberate and also like, filtering, right? High pass filter, low pass filter to avoid those noise interference. But the problem is like, when the signal pass through your human body, some of those high frequency parts, they are actually missing.
I
So
see.
essentially, yeah, the conventional signal, we cannot like, recover those missing parts.
I
So
see.
that's actually the motivation for us to use a deep learning method there. Yeah,
All right. Thank you.
sure, sure. Thank you, Misha.
We might have question time for one very short question. Otherwise, we can sort of end it here and give our thanks to our speaker today, Dr. Longfei Shangguan, and our next webinar will be on November 20th. So if there's no further questions, I'll leave it at that. And thank you all, and we look forward to you joining for the November 20th webinar with Anna Barnaca. Thank you all.
Thank you.